Let's start with the problem. Fine. Yeah. On this thing. Okay. Okay, so I'll start my talk, and some of you are new, can be new, so I'll just go through this ancient mathematics, and this is just first verse of Ganitapada of Aryabhata, and here Aryabhata is challenging the seven planets in some sense. And then these are the names that we discussed. We have 8 names here, and Bhaskaracharya has given 18 names. So that I mentioned last time. And these names given by Bhaskaracharya, they are the popular names and they are available now. Some of them are here. Mahapadma should be used very much because it is 1 lakh crore. So Chanku, Jamji, Ante, Madhya, Parartha. Parartha is 10 to 70. So these names have been made by previous mathematicians and they are now finalized. After these names of Bhaskara, there are no further names. Okay. So million, billion, trillion is 10 to 6, 10 to 9, and 10 to 12. And these names are here. 10 to 6 is Dasalaksha, then 10 to 9 is Abja, and 10 to 12 is Mahapadma. Now we talked about Varga. So Varga has 2 meanings. One is a square, then its area, and also product of 2 equal numbers. That is Varga. Similarly, Ghana or cube, it has 2 meanings. One is the cube, and in English also we have cube for product of 3 equal numbers. Then how to find the square root? So this is what we were discussing last time. So to find the square root, we have this number like 625, and this is Vargasthana, this is Avargasthana, this is Vargasthana. So Vishavasthana, 1, 3, etc. They are Vargasthana. Samasthana is Avargasthana. Now, if you take a number which is a perfect square, then how many digits should be there in the square root? So the number of digits is equal to the number of Vargasthana, square places. So in this case, 625, there are 2 square places. 5 is one number, first square place, and 6 is the second number, which is the square place on Vargasthana. So there will be 2 digits in the Vargamoola or square root. And the method of Aryabhata is the following. First of all, you take the largest possible Vargasthana. So 6 here, it has value 600 actually. It is there, and then you subtract maximum possible square from this, each square of a digit. So 2 square, and then that 2 square root of this you have to write here 2, and then multiply this square root 2 by 2. So it is 2 times a. So this is a, some number whose square we will subtract, and then we get remainder as 2. Then take the next digit 2. After that, we are dividing by this 2 times a and finding the quotient. So quotient is 5 here. Now here actually we are having some extended quotient. So this sometimes this 5, instead of that we may write 4 also. So that some examples of that we will see. So 22 minus 20 is 2, and then take the next digit 5. After that, you subtract square of this 5. So 5 is written here. So first of all, this 2 is written here. Now this quotient 5 is written here, and you take the square of that. Now after subtracting the square, you get zeros, and there you stop, and you have got the square. So in algebraic terms, we can say that we are subtracting first of all. So we are first getting this 2, that is A, then 2 times A. You are dividing by 2A and getting B, and then AB, we write here, AB, and then subtract B square and you get 0. So this is another example in which there are two numbers, 2 and 1 0. So there are groups of 2 here because we are finding this table. And the same procedure works. So 3 square is 9, then 3 into 2, 2A. So that is 6, and then after taking this 2 here, the quotient is 2 here, and subtract 12, then you get 0, then you take 4 from there, and then this 2 square, same 2, I have to take 2 square equal to 4, I subtract and I get 0. So this procedure is important, and if there is a round quantity there, then you have to move ahead with the same procedure. So how it is done, let us revise, because this is what will give us how to find any numbers. So this is a larger number in which there are Vargasthana 6, 7 and 5. There are 3 Vargasthana here. And therefore the Vargamula or square root, we have 3 digits. In this case there are 2, 3 and 4. So procedure is the same, that first of all you subtract a square, here it is 4, and its square root is 2, which is written here. So Aryabhata has written that separately you write this square root. Then square, 2 square is 4, subtract, you get remainder 1, take the next digit. Now 1 4 you divide by 2 into this 2. So 2A, you divide by that, and you get 3 as the quotient, 12, subtract. Now this 3 is to be written here. So 3 is the new digit that we have obtained in the square root. Then you get 2 here, then take the next digit 7. Then you have to subtract by 3, subtract 3 square from this. So 2A by 2A you have to divide, and 3 square you have to, means A square you have to subtract. Once you do that, you get 18 here. So this is 3 square is 9 here, subtract. Now 18, then take next digit is 5. Now you have to look at the 2 digits that you have got here. 2 and 3, these are 2 digits. So this is A and B, 2 digits we have got, A and B. So multiply this number by 2 and divide by that number. So 46, you should divide by 46 and cross. Then take the next number 5, quotient is 4, subtract this product 184, remainder is 1, and take the next digit is 6. Then 4 square can be subtracted and you get 0. Now these 2 steps are to be done one by one. That divide by 2A, one thing, take the quotient, and then subtract the square. So then the third, so this 4 also we have written over here, and that is the Vargamula. So ABC. So this is clear. This same thing I have done here. Now cube root. If you want to find cube root, what you have to do is same thing you have to do, but now your roots are of 3 digits. So 17, 5, 76. That is the example that we have. And 26 is the cube root here. Now first of all, 2 cube can be subtracted on the Ganasthana. So 7 is the Ganasthana. 7 is the Ganasthana, and this is first Aganasthana, 1. And here 6 is the Ganasthana, 7 is first Aganasthana, 5 is second Aganasthana. So 2 Aganasthana and 1 Ganasthana. So in the fourth power, fourth, if you want to find out, that there is a place which stands for the fourth power. Then there are 3 terms which are not the 4th power. So 1, 2, 3 numbers will be there. Okay. Now, as far as the method is concerned, you take this 2 which you have written here as the first this digit in the cube root. 2 square into 3, that is 12. You divide by that. You divide by that and get 6. 6 and right here, 26. So now 3 to 6 square. So that is 3 into 2 square into 6 is 72. Subtract, then you take this 7 and then it is like 2a square and this b is there. Then once b is obtained, you use that. So 3 into 2 into b square, 6 square. So that is 216 which we subtract, and then this 6 cube you subtract, and you get 0 here, fortunately. So what we are doing is, if you use the expansion of a plus b bracket cube, then a cube is there first of all, which we subtract. Then to find out b, we divide by whatever base, divide by 3 times a square and you get b there. Once you get b, you also subtract. So we have already subtracted 3a square b, that is 72. Now you subtract 3 times ab square and then finally you subtract b cube. So it is given by capital N minus a plus b cube. Roughly it is like that. So now this is another example, but where even if there is a decimal point somewhere and the number is not a perfect cube, the method of wherever you work, every time you have to get. So from this Ganasthana you have to decide that because it's 176.76. So this 6 is the Ganasthana and these 2 are Ganasthanas. And 5 is the thing. After that, you must take zeros on the right hand side. So you can have the next. So it is, you can assume that this number is 176.760. And then by the same method, you can find the cube. So this thing I should put somewhere else, maybe here. You can minimize, but we don't see others. So there are other people also who are there. So Deepa Krishnamurthy is there and Sachin is there. Sachin was a student who was doing study here yesterday, so he is also here. So now here again we see that whatever decimal point etc. is not very important here. Okay. So this is the same. This is a larger example. 1860867. So Ghanasthana, Aghanasthana, Aghanasthana, Ghanasthana, Aghanasthana, Aghanasthana, and Ghanasthana. So that is how, because there are 3 Ghanasthana, there will be 3 digits in the cube. That is the thing. And then you are first getting this 1 because you are subtracting 1 first of all. Then you are getting this b by division. So 3 times a square you are dividing by. 3 times a square you are getting b. Then you are subtracting 3ab square. Then you are subtracting b cube. So actually you are subtracted so far a plus b cube. A plus b cube you are subtracted. And then you are trying to get some c there. So for that, 3 times this a plus b. This is 12 is like a plus b. So place value is also involved there. So a is either 1 or 10. You have to take appropriately. So now you divide by 12 here. 3 into 12 square. So and then that gives us c here. So this 3 is actually c. And 1 to 3 is the cube. After you get that, 3, it is like a plus b into c square. Then you have to subtract 3, this is a plus b, and c square you have to subtract. And finally you are subtracting c cube. And then you are getting 0. So this is actually a plus b plus c bracket cube, kind of. where A is their which place value they are actual value of that will be connected. A is A00, like that. B is B0. So, but only digits are A, B, C. Values can be, and these values are actually placing the numbers at the appropriate place. If you place A here, then value A is 0. Place A here, then A is 0, like that. So it depends. The value of A, B, C, etc. is achieved by putting it properly. Okay. So now, yes.
Can we say that what is the places of future we have got? You take it as a number and then 3 into that square and the next number is
Yeah. So by placing that appropriately, this whole thing is achieved by Aryabhata.
How many much power is indicated actually? Because otherwise,
Okay.
so otherwise, then there can be a claim that binomial theorem.
Binomial theorem would be used here when you want to find out that the fifth for example, you want to find.
Was it no?
Pascal has already stated Pascal is here. Pascal triangle that was Virup, and during Virup was for Finger. Finger had become from Pascal triangle in the third sentence. Yes. So he has mentioned that you arrange a square first of all on the top. Below that you put 2 squares. Below that you put 3 squares like that. Once you do this arrangement, then you put one on the left side and one on the right side. Like that. Once you do that, you just add 1 plus 1 equal to 2, 1 plus 2 and so on. This is very clearly described. Exactly. Here is that 2 square on top of that 1 square. And this is called Veru cluster. Veru is like a mountain, Veru cover. And then cluster, as I understand, it must be the layers of layers of that. These are the layers of Veru. So this is how I already done the structure of the Himalayan. And he required all of the movements there. And these binary variations were two. How the person with Aryabhata Buddhas given the method of science the person was how to do that. It is something he knows. And by these 2 examples, the method of Aryabhata is very clear. So suppose you want to find out people, what Aryabhata will do? First of all, he will have groups of 5, starting from grid place. So then it should 0, 1, 2, 3, 4. So those 1, 2, 3, 4, they are non-Pancham. And this is Pancham of place. 1 is 2. So we next we again Pancham place, Pancham Sthana, there is a Pancham. There are 4. So we find out how many Pancham Sthana are there. How many places for fifth power are there. So if there are suppose 15 digits in our your number, then there will be 3 Panchama Sthana places. If it is 16, then there are 4. So 17, then again there are 4. Because the 16th number is again Panchama Sthana. So first digit is Panchama Sthana, 6th digit, that is Panchama Sthana. Again, everyone the digit is Panchama Sthana. And 16th digit is Panchama Sthana. There are 4 Panchama. That means you want to find 5th root, then there will be in this case 4 digits in the beginning of that given number. So given number has 16 digits and you want to find 5th root. So Panchama Sthana are 4 there. Therefore, there will be 4 digits in the 5th root. And then how many other ones you method is same. That is first of all you will subtract from the largest digit. Largest digit is maximum. There he goes. And subtract 5th power. Okay, 5th power. Maximum possible 5th power is subtract. That is 8. So 8 is 5 to subtract. Get the remainder. After getting the remainder, get the next digit. And then you should divide by. Now, I u times a raised to 4. I u times a raised to 4. You should divide by that. And let b. Okay. Now, here there is a catch that in the usual case, you try to maximize that b. But because there are so many things subtracted later, it is likely that the usual B may not work, and you may have to take B minus or maybe B minus 2. You don't know that. That is the only catch here. But otherwise, you are dividing like equal to B, and you are getting this B. Once you get B, immediately you start using it. So far we have subtracted a raised to 5, then we have subtracted 5 a raised to 4 into B. This time when you divide it, you do that. Then you will subtract 10 a cube B square by taking the next digit. Then you can subtract 10 a square B. Then again take the digit and subtract a b raised to 4. Then you can subtract b raised to 5. Now, if you may go ahead because the number of digits is 2, then you are 2. Because we get remainder 0, if the original number is perfect square, perfect power, then you are 2. Otherwise, you will go ahead. To go ahead means what? Whatever remainder you have got, take the next number there and try to subtract maximum possible. So, therefore, what we will do? This is now like a plus b we have obtained so far. A plus b. So we have to we have to this. This is in this example you can see this frame is there. This is like a plus b. You see here, a plus b. This frame was here. So once you are subtracted in this case cube, so there we subtracted fifth power and got something. Get the next digit like 8 we have got. Now you should divide by, in our case, 5 a is that number like 12 here. That is to 4. 5 whatever you have obtained in the fifth mode place. So far whatever you have obtained like 12 here. So that you take its fourth power you should take and you should divide by 5 that number like 12 raised to 4 divide by that and get the quotient. That quotient is C. Third digit. Once you get C, you start using it. So you subtract 10 times a plus b raised to 3 into b raised to 1. Then you subtract 10 is a plus b square. A plus b is that together that number. And then you can continue with this. And this will work. And somehow I do not see, do I have this calculation? I do not see the calculation. Just to show you I have done some calculation, but it has not come in the file. But okay, so what one is using is, shall I see this? I open. These people are able to see, so I can write here. So, not this. This one. So, first of all, A plus B. Let me talk about. Okay, Q is a Q plus 3 a square b plus 3 ab square plus bq. So these are two digits in the cube root a and b, and our number is a plus b cube. So first of all, you are subtracting a cube by trial. Then after that subtraction, you know a, so you are dividing by 3a square, get b. Use that b again, subtract 3ab square and subtract b. So if you have two digit cube root, then your job is done by this formula. But suppose there are 3 digits, then what happens is a plus b plus c bracket 2 digits. Now this is, first of all, you do all this procedure.
A plus b.
No, no. See, what you are saying is actually correct, but I would not like to write that, because then there are lot of confusion in this. So this A is actually here itself you want me to write 10A plus B, that's right. But what I am saying is the value 10 is achieved by putting A in the right place.
Okay, but 25 was 7, 20 plus 5 was
20 plus 5 years.
Ah.
So this is actually 10A. You can take it down. In the calculation, this is not same. That is how the calculators are arranged. That you write A here or no. Okay, you put B there or no, like that. So you are arranging the calculation in such a way that this A is a digit, there are digits, but their values are actually 10A, like that. Later on, it will be 100A plus 10B plus C, it will be like that. And that value is actually by the place value. By appropriately using that digit, this specific place. So, in both calculations, you have to place everything properly. You place as well as properly go on. So that is why.
Now, who has first started with the place value? Because if Aryabhata has started with place value, actually he should not use it with such a ease. I expect the students to know it and do it with such a ease.
So, students have a problem. You will see a problem. Maybe the place value is older than that. This is some of the order.
And Bakshali because in between
Bakshali is later on. Aryabhata is
23rd century is someone or
Bakshali. Yeah, Bakshali is supposed to be the third century in India. And then there are some other, so, yeah. So, in any case, what Aryabhata says is that I am telling you what is well known. These words are that Sanmanitam Jnani. Kusum is Sanmanitam Jnani. So, whatever we described here already in Kusum, that is part of that I am telling you. So, this is already well known. So, you can think a textbook kind of. So, now what is happening is you are doing the steps here. First of all, you are subtracting this A cube, then you are getting B, then you are subtracting all these things so far. Okay, when you get the first two digits, you have done that. Now I want to get the third digit. So for that, I have to go further and do the calculations. So now you have arrived at A plus B. A plus B means 10A plus B. You have arrived at, because I am writing A and after that I am writing B. So that is 10A plus B. So this is now I want to get C. So what I am doing is plus this is 3 times A plus B bracket square into C. So after subtraction, I am dividing not by 3B square but 3A plus B square. A plus B is juxtaposition of A and B, that is like 12 in that example. So 3A plus B square you divide whatever this minus this is divided by this, so you get C. But C the approximate because only other things are there. So once you get C, you can now subtract further 3 into A plus B into C square, and further you subtract C cube, and then you get 0. Then you get 0. But if the number has 4 digits, then this whole thing will be A plus B plus C plus D bracket cube, and you will do all these calculations, and what we have subtracted so far is A plus B plus C cube. This whole thing is A plus B plus C cube. That is, and that I have already subtracted. So all these things together, which stands for A plus B plus C cube, then what we should do? Plus 3 times, this is A plus B plus C. So this A you can now take as 100A plus 10B plus C like that. But in the actual demonstration, these are used as digits and kept at appropriate places into raised to 2 into D. So divide by 3 into A plus B plus C square. That's what we are doing, because the juxtaposition of these numbers we are using. And then you get D. Once you get D, you again subtract 3 into A plus B plus C into d square and then again subtract d cube. So if it is a 4-digit number, you actually got this cube equal to a plus b plus c plus d cube. You have got the correct. And so now the method is very clear that we can do like this for 4th root, 5th root, 8th root, any root can be obtained by the same. Only thing is when you divide by such a number, like in the 5th root case, you will be dividing by 5 times this whatever you have obtained raised to 4, you will divide by that. Or in the nth root case, you are dividing by at the beginning 5 times or n times a raised to n minus then you get b. That is the only change. Otherwise, this is a kind of identity that we have obtained. So, if you want to write the identity again, write on this a plus b plus c plus b bracket cube is equal to a cube plus 3a square b and so on, plus 3a plus b square into c, etc. plus 3a plus b plus c square d plus b. This is the identity. And this identity can continue is important. That whatever processes we have done earlier, they are not lost. They are useful. You can just go ahead and if all digits are there, you can use this identity. That is the basic trick in this. So another importance of the method of Aryabhata is that even if the given number is not perfect cube or a perfect clean power, the method will work. And you will get kind of approximate cube root or big root. And also you can put a dot there, decimal point, and you can go ahead with the same. And you can find out cube root with the 2 correct decimal places of 3, whatever you want. So you can continue with that. It is possible. Now this is when you so actually Aryabhata gives it for the situation when the given number is a perfect power, perfect 4 power like this little one for a power. But
because knowing you also need squares and lower.
yes, but these numbers are known to you, so you can calculate this.
Don't even need
What is that in the process? Yeah, in the process, because up to this you have inductive, you are going ahead. This any number of numbers are there, you just go ahead. So, so this is the importance that which we can tell the students that even if it is not a perfect cube or perfect shape or then other calculations are to require number of decimal points. Although calculations will become more complicated, but it is possible and
calculations do not get complicated. The iterations increase. The iterations will increase. For one cycle, it is just repetition.
yeah, but number of data is more. These are more. So now this is better, but now can you use this method to find 23rd root? The number. Why am I saying 23rd root? Because the problems are by we want a 201 digit number. So if suppose how Aryabhata will lost. You can do it in 90 seconds because this calculation of getting 23rd root of a 201 digit number. 23rd root of a 201 digit number was obtained by in 90 seconds in 1975. So how so she will not do Aryabhata, but she will use only one important thing that number is a perfect regular form. So that is one important assumption there. If it is not a perfect 23rd power, then Aryabhata's method you have to use. But if we are given the 23rd perfect power, then we can use some things. And these tricks we have learned in the high school also for small numbers. So find the square root of 625. So at the end it is 5. That means the last digit will be 5. Okay. And the square root has 2 digits. So one more digit you will find out. But then 625 means if you have this group of 2, then one could be of 6, another is 25. Another 6 means you should subtract larger part of square from that. So that is 4. So 25 is balanced. 625 is square root is 25. Here we are using this in the perfect square. Otherwise, and we can say 625 are 1 by 5.
But it is, in 23 is a prime matter.
It's something matters there. Because we are also take her because we are not. But so what is required is, and the theory is that we can use a method that I don't know what she has used. I don't know what method what I am using. So we require that 23 should be an odd number, which is and not 85. So it is relatively prime to 10. So this power should be relatively prime to 10. So that is what is used that we can see easily in some. So wiping out law
You think she used 23 at the time?
no. She clearly with
And she explained everything? And she explained everything?
I do not know whether but one can understand what that is can do. Which I will explain. So first of all, I should remove this. So there is something there. This is the error, or you can just rotate it. That is also possible.
There is a part that is
Pages there.
and this will be stored.
Okay. So pages. A new page has come. So the method I was saying for square root as the then I should again click here. High school method. So if I want to find the square root of 625, which is a perfect square, then this 6 gives 2 and 5 gives 5, because square root is 25. Okay. Because only if this ends with 5, then only the square will end with 5. So this is all. But if I have some other square, so 9801. This is the number 9801. Again, so this is one group and this is another group. And 9 is a possibility or 1 is a possibility. So there are 2 possibilities. Okay. Now from this we get 9 square is 81. So I should subtract 9. I mean, take 9 here. So these are 2 possibilities of square root. Which one is correct? This is correct or this is correct? So the trick for that is you should, so our teacher would write like this 95. So 95 square is equal to, so the trick for 95 square is 9 multiplied by 10. Next number is 90. So 90, 25 is the square of 95. And this is larger than this, therefore this is correct and this is not correct. So for the square root, there are 2 possibilities which come from the last digit. And the first digit is obtained by figuring which square can be subtracted. And then choose the square of the in between number ending with 5. And this is larger, therefore it must be 99 square. 9801 is equal to 99 square.
I specifically 95.
Hmm?
I specifically.
Because you know which numbers will give the same square. So you see 10 minus 1, 1 and 10 minus 2, 2 and 10 minus 2. They will have the same ending, it will square, right? Because minus 1 square is plus 1. That's why. So in between number is 95. They, one of them will be less, one of them will be more than that. Because of that. So that is the school method. And here,
Let me say 95 between 91 and 99. And we know how to get the 97. So you can just compare that and get it.
and what you are saying is it always happen like this? As far as question. One of them is above and one of them is below. One number is smaller than 95, one number is larger than. That always happens because one number is just A and another is 10 minus.
I think
2 and 10 minus 2, right?
no, absolutely, squares of single digit number.
Clear the figure.
That you have to know.
That and you have, you should work with it, basic data. So this is the high school method, and you already are the problem here between your topics that because that we are in the problem. Because we never find the next step. Next step is finding Q by high school method. That is simpler than this. Why? Because 3 is the number of 3 times 10. If 2 is not there, then it is 10. That's why you have a problem with 2. But we do not have a problem with 3. Okay. So you can take a cube now. I will take another example 1, 2, 1, 7, 2, 8. So 1, 7, 2, 8. This comes to a taxonomic number. That's why you know that it is 12 cube, right? So this is 12 cube. How will you find the cube root by high school method? So first of all, this is one group, this is another group. Okay. So for cubes, what happens is all these numbers 1 cube is 0, 1, 2, etc. 0 cube is 0, 1 cube is 1, 2 cube is 8, large digit, 3 cube is 9, 3, 7, 7, like that. So these are distinct digits. Unit places are distinct for cubes.
Okay, because 3 is prime 10.
3 is prime to 10.
That is why I guess that's later.
Yes.
Yeah.
3 is prime to 10.
And
That's right. Otherwise,
if we can algorithm, they work.
there. Exactly. So now because of this, so first of all, you can, that's why I am saying that 2 and 3 are different things. 2 and 2. And one of them 2 is not prime to 10 and 3 is prime to 10. So 3 is simple. Why? Because now this is 8 and 8 corresponds to 2. So I immediately get 2. Okay. And then this one I am getting from the initial one. So that is how. So I will say that this is Aryabhata. This thing. And this is Shakuntala. So the point is that you can also find Q by the method of Shakuntala without doing the method of Aryabhata. That means the digit 1 also you can find by the same. How? So for the last digit we have used this 8, right? For the digit 2, to obtain that we have used 8. Now you can use this second last digit 2 to find out this one. That is the method of solution. And that works. So in general, if you look at the number,
What's the configuration here?
huh?
I am not following.
There are another, I am taken completely, that's also true. But I am only saying right now that here from this last digit I have got last. And one can also get this last but one digit from this last but one digit.
You are just at the. But it's not very very.
I can prove it also with it. And it is important to do that so that what will be done by second order will be clear. If you do this thing, then second order will be perfect immediately. But what she has to do, that's what I am let me explain first. So second order has 201 digit number, and you want to find out 23rd root of that. Okay. So we are saying that she will have all of the change pay because so many things are done. So many numbers have been constructed and they should be subtracted and so on in so many ways. These are all very large numbers. One number itself 201 digit number. So it will not be, it cannot be done for anybody. Maybe computer by Aryabhata, that is possible, but we has run back in the middle of this time. So first of all, second we should determine how many digits are in the 21st group. Okay. And in this case, like Aryabhata does where the square root and cube root, you should divide by 23 here, and then if you find the quotient, then you must add 1 to it required. So how many digits are there in this? You can find out that 23rd root has 9 digits. Okay.
I am finding it very root of.
No. This is digit number. Yeah. Shakuntala Devi was given a large number. That large number has 201. And this year she needs to find out the 23rd root of that. Okay. So for that, she has to use the method that I am explaining here. That these 9 digits will be obtained not from those digits which are very large, but the digits which are very small they will be used. That means she will use initial 9. So what she will do is initial 9 digits only are used. So she is being calculated exactly after that. And therefore, our actual is very probability change any number is our plus. Very possible, but when you are given that in the pocket, that is our power, then the minimum probability will go up. And you will get the answer very quickly. And this calculation figure is very fast to make that task. That is also
consider the whatever. Now 9 digits are there. A0, A1 up to A9. Now, if you do whatever power, whatever the expression is, just one step before, will contain all the power, all the numbers. A0, A1, A2, A3 up to A8 आणि त्याचे 23 पॉवर केली तर काय येणार 23 आणि समेशन काय पॉवर असतील त्यांची बेरीज मात्र तिकडे कुठलाही एक नंबरची पॉवर 0 नसणार म्हणजे इनडायरेक्टली प्रत्येक नंबर अलीकडच्या नंबर मध्ये आहे सगळ्यात शेवटचा समथिंग लाईक
So what is going to happen is So now I will make everything clear by writing an algebraic step. So suppose, okay, or we can calculate this thing. How we can find the cube root here by using the last two digits. Okay, here, how we do it? So you have to say that our number capital N is 1728 and 2 we have already found out. So I can say the cube root is 10a. No, I'm taking this as a digit plus 2. Okay. So cube of this is equal to this. This is what we have got. And then 28 therefore is common to 10a plus 2 bracket 2 mod 100. Twenty-eight is common to 28 plus 2 mod 100. And we can solve this. That is the point. Because 3 is relatively prime to 10. So we can see this is common to now 10a. So 10 cube, I don't have to take that 3 times this square, that also I don't want. So 3 times 10a into 2 plus 2 cube. This is 28. So therefore 20. So this 28 is here and this is 8 here. So that goes, and therefore we get 20 is equal to this is 60 a, that's all, mod 10 mod 100 or 10 now. 10 means only 100, but I can cancel 0. So is it okay? 28 subtract 8, so we get 20. And what remains here is 60 times 8. So we get 2 is common to 6. 6a, oh sorry, mod 10, because that 100 will reduce to 10. So we can now cancel these 2 also. So 1 is common to 3a mod 5 and a is equal to 2. Wrong, something wrong. I want 2 square. Yes, thank you. There was a mistake here.
Minus 3 divided by 5.
This 60 will become 120. This will be 120. Now this is 120 means here it will be 12. And then we can cancel this, so it becomes 6. So a is equal to 1 and that 1 is there. So this method works. So basically, the last two digits of the cube root are obtainable from the last 2 digits of the original number. This is what, but this is quite general. So I can again take a new page.
I think it seems to me that it's not only for decimal system, but for any
System one can
any base
here the method is 10, so also the combine that base that power to require some condition of that type.
Okay, those are very good exercise.
Just to try to. So basic idea is that so now we take any general power. So suppose A is congruent to B. Mod 10 raised to K. Then A raised to M is congruent to B raised to M. mod 10 raised to k. So their k powers will also be congruent to each other. And now suppose m is coprime. So now suppose m is coprime to 10. I should write 10. 10 is fine. M is coprime to 10. Then what happens is, now this is number 10. Then what is phi of 10 raised to k? Euler's function. So Euler's function is actually phi of 10 is 4. Phi of 100 is 40. And then you multiply by so 4 times 10 raised to k minus. Phi of 10 raised to k is so this has again 2 and 5 as the factors. Phi is like this. Phi of 10 raised to k. One moment there is some number also, but at least we can say phi of 2 raised to k into 5 raised to k. Integrate will be fine. Yeah. So now this is 2 raised to k minus 1 into phi of 2. And 5 raised to k minus 1 into 5, which is 4. So this is 4 and this is 1. So it is phi of 2. Phi of 2 is 1. Now it is 2 raised to k minus 1, 5 raised to k minus 1, 10 raised to k. This is so now what is happening is 4. This I didn't write properly, but phi of 5 is 4. Phi of 5 is 4. All right. Oh. This is 4. So now it is this area. Now, therefore, M is, this is interesting step that M is coprime to phi of 10 raised to k. This M, because it was coprime to 10 before, but it is also coprime to that. So I can find out M is M times say M1 is congruent to 1 mod phi of 10 raised to k.
This because M is odd.
See, M is relatively 10 to 10. So it is odd as well.
But now 4 and
They have 2 and 5 there.
no.
They have 2 and 5. Sometimes it is high and it is not. But here it is not happening.
Puskai bonala, 524 puskai.
This is something interesting. And therefore, it is coprime to this number. Okay. Now, once M is coprime to this number, I can have M1 congruent to 1 mod phi of 10 raised to k. Therefore, this is equal to 1 plus 3 times phi of 10 raised to k. Okay. So what I have no onwards. Now this is one way we have done. So I want to do the converse. So let A raised to M congruent to B raised to M mod 10 raised to k. Mod 10 raised to k. Huh. She must have generalized for high school method, that I mentioned cube kind of thing, that mod 10 raised to k. Okay.
Clean दिलं तुम्ही. आता
पण-
तेच काय.
So this raised to m1 is congruent to this raised to m. A raised to m raised to m1 is congruent to b raised to m raised to m. So let me write that. A raised to m raised to m1 congruent to b raised to m raised to m. Mod 10 raised to k. But m1 is equal to 1 plus p times pi of 10 raised to k. Okay. Now, in our method, which we use, there are some problems after this what I want to write. So let me explain that. So suppose I want to deduce from this that a raised to pi of 10k, 10 raised to k is 1 by Euler's theorem. Okay. A raised to pi of 10 raised to k is 1 by Euler. So I can forget that. And I will get A congruent to B mod 10 raised to k. But there is a small catch here that in understanding require A should be congruent to that number.
So it's very static.
No, I didn't say anything about A and B. I said about the power n. Okay.
Stackers, suppose A equal to B mod 10.
No, this is done. This is done. This is done. Now I am saying the converse. Suppose I start with this and I want to get A congruent to B. Okay, that is the converse problem I want to deal with. Where you assume that M10 equal to 1. This is what I have done so far. Then I derive that M is also congruent to pi of M. Therefore, I can raise it to M power and get A congruent to B because M1 is what 1 plus P times pi is. But A raised to pi of M raised to K is 1. Okay. But therefore, we require that A should be relatively prime to 10 raised to K. That means A and B they should be even, not even, and they are not even required. So what will happen is there. Suppose you start with even number and you are asked to find out whether to even what will but that is not the problem. Hospital show that we can have that to factor we get it out that. Right? Similarly, if 5 is a factor of that, if the is 5, then 5 is to be a factor of that. So you get it out that. So you arrive at a number which is an odd number and the result is 5. And then it's 25 to be. At least we can assume that A and B they are odd numbers and they don't make it 5. And then you get A congruent to B mod 10 raised to K. So now what that essentially shows, this is true for every case. That actually shows that on the last digit of the original number, given number capital, which vector will be given, you can get the first digit of the critical root. The last digit of capital line will give you last digit of the root. Second one digit will give you second one because congruent mod 10, congruent mod 10 every time you will get one, and every time you solve one equation, which is like A congruent to B mod B. And then we can get by this. So there are some steps of this type that we reduce the problem to the given number of group you have find out. It should be congruent to that, and power also be congruent. If found not defined, then you will have to problem next square root problem. And these will have possibility to further discuss that case if you want to simplify. So suppose that we is slowly finding out the last 9 digits using the last 9 digits of the big 201 number, 201 digit number. He is concentrating only on the last 9 digits. And then he is finding out, and for her this is very simple. Only digit now. You know, see, because it is a 201 digit number, but you are not using the very one top. So these two methods are there, both methods are important, but here there is some mathematics which you have to manage to use. And okay, so now I should do, put this down. So this is fine. Time is also over. So we will stop now today. So what we have done is, today we are seeing that we can generalize the method of Aryabhata for square roots and cube root to any nth root. And you can use the same method to find out any nth root. And if you already know that the given number is a perfect square, cube, or 23rd power or 39th power, then it is easier to find out the root by using the initial digits, not the final digits. So these two things we are seeing. So next time we will see more about the methods of Aryabhata, especially geometrical methods. Okay. Thank you. Okay.
So,
Yes. Yeah.
this is stop.
Stop.
Stop recording.
Stop it.